Everybody. It's me, Dr. Kopcha. I am a professor of learning, design, and technology here at the University of Georgia, and I am here to give you a brief introduction to my scholarship, but also how I got to where I'm at right now with my scholarship and what my scholarly journey looks like. So sit back and enjoy the ride. Um, I started as a classroom teacher. I was a math teacher in Connecticut. I did 3 years of high school and 2 years of middle school math. And I was really into technology. I liked integrating it. I had my students doing all kinds of fun stuff with online tools. And this is back in like the early 2000s, so the tools weren't that sophisticated. But a consistent message that I got as a teacher was that technology was going to save us. It was going to make learning better. It was going to make this better. Everything in education was going to get better with technology. And so I went into my grad studies really with a question of like, does technology really improve learning? I kind of wanted to prove it. I wanted to set up scenarios where I could test whether technology was better than not technology. And so I looked for studies that did things like that. And I wanted to know what the research said. That was really where I was coming from. And over the course of my career, I have found a number of studies that compare technology to no technology. Good, solid experimental research, randomized controlled trials, just like in medical research. These are really important in education. Uh, it's Slavin is the gentleman's last name. Dr. Slavin has worked with the education department, the National Department of Education, working on what makes good educational research. And from his perspective, it's that medical model, experimental studies. You compare a treatment group to a control group or a placebo group, and then you compare them and you have a lot of tight controls so that you can tell whether or not something is making a difference. Sure enough, I found a study, Pasawa and Valdez. They did an experimental design, random assignment of treatment, meaning technology, and then no treatment, a control group. Look what they found. There's a difference. Students who get the technology were doing better on standardized tests at the end of the day than those who didn't. That is exactly what I thought was going to happen. Fantastic. Let's go look at another one. Ah, dang it. So here's one by Shapley and their group. They randomly assigned to 21 middle schools a technology immersion model. Everyone got laptops and had laptops the whole time. And then they had 21 control schools. No difference. Oh, come on. How can that be? I just found a study that said that there was a difference. All right, let's keep looking. John Hattie has this incredible book. It's a synthesis of meta-analysis related to student learning and achievement. And he wanted to know what makes a difference, what really makes a difference and influences student learning. And he looked at all these factors. If you look over to the left of my screen, those are all the factors that he analyzed to see what truly makes a difference in learning. And I want you, like maybe with your finger or your eyeball, like, where do you think technology is in that list? It's a big list, right? But just take a second right now. Where do you think technology is? Okay. So I'm going to show you the top chunk. These are the things that make the biggest difference according to John Hattie and his research. Teacher efficacy, cognitive task analysis, that's our field. Piagetian programs, things based on Piagetian development, stages of development. Jigsaw, that's a great group technique. Self-efficacy, teacher credibility, classroom discussion, scaffolding. You know what I don't see on this list of the top things? I don't see technology. Okay, so then the question is, where is technology? If you said technology was at the top, okay, make another guess. But keep in mind where you think technology is and have a look here. Yeah, it's all the way down there. Oh my God, like, how can that be? Technology and math. I was a math teacher. I know what makes a difference. How could it be that far down on the list, right? Web-based learning is even lower. One-on-one laptops is even lower. Are you kidding me? What is happening here? Why? Why is the answer sometimes technology makes a difference and sometimes it doesn't? And then recently, I saw this floating around Twitter, and it really captures the answer to the why. Why does technology sometimes make a difference and then sometimes it doesn't? This quote is great. Measurement is not the same as understanding, and art knows that better than science. And maybe, just maybe, treating the phenomenon of technology and technology integration and technology for learning, if you treat that phenomenon like an observable, measurable thing that you can study through hard science, maybe you miss something. Maybe you miss a deeper understanding that goes with the effective uses of technology, which is why sometimes it makes a difference and sometimes it doesn't. And that brings me to my revised questions. I no longer want to set up studies that test whether technology makes a difference and if it's better than no technology. I don't find that as meaningful as the part that art knows better, the understanding part. How, when, why does technology really improve learning? What does that look like? And how can I be part of that? That's an exciting thing that I get to do. And so that led me down this path towards reading more about embracing complexity in educational design, but also educational research. A lot of the scientific methods of measuring tend to reduce the complexity of a phenomena in order to study it. You have to do it in a laboratory, or you have to strip away certain conditions that exist in the real world in order to create an environment that can be tested using a medical model of research. Well, if you read about complexity, that reductive approach simply it undermines your whole point. If you remove the things that make something complex, you're not really studying the thing in the first place. Complex phenomena must be studied at their levels of emergence as they're happening, not in terms of subcomponents, and certainly not little fundamental particles like dividing up educational phenomena into all these little pieces, but understanding what's happening as a phenomenon emerges and really studying that and those moments. And in our field, how we can design environments or design technologies to really have an impact at that moment of emergence. And so part of how I got here comes from my background as a teacher. I taught math. I'm fascinated by how math is developed and used by human beings. And chaos theory was a big part of this. I loved chaos theory. And if you don't know anything about chaos theory, you should do a quick Google search. It's basically a branch of mathematics that looks at underlying patterns, but nonlinear patterns of behavior, random things that are happening, things that are somewhat unexplainable by regular mathematics. So a good example, Edward Lorenz. He's not a mathematician, he's a weatherman, but he's famous in chaos. And the reason why he's famous, he was trying to create a group of equations that would mimic the behavior of weather patterns. And he was trying to predict weather using this group of equations. And his goal was to take the local conditions from today, enter them into this set of equations. So, humidity, temperature, all that stuff, spit out a prediction for tomorrow's weather. Take that, put it back into the set of equations, and then predict 2 days out, and then 3 days out, and 4 days out. And he was trying to get it to see how many days out he could accurately predict the weather. If based on today's conditions, he could accurately predict 3, 4, 5 days out. He found out two things. One, you can't. That's the first thing. But he was open enough to realize he was discovering something, a new phenomenon in mathematics. And so this is a result that comes from one of his groups of equations. It's called the Lorenz attractor. It has 2 points of attraction. And when you enter a certain set of numbers and you graph what happens around that, you get a pattern in which no 2 points overlap. It will go on and on and on in this infinity type shape without ever crossing over itself. Fascinating. Benoit Mandelbrot. This is a Mandelbrot set. He's not necessarily a mathematician. He was using mathematics in order to come up with a formula that could accurately predict and replicate the shape of any coastline based on other features. You can even see how that looks a little bit like a coastline. There are parts that repeat. There are parts where if you zoom in really small, it looks almost the same as it did when you zoomed out and looked really big. He came up with this incredible, just really incredibly beautiful set of artwork associated with chaos theory from that goal of something that was real and applied in the world, and it turned into this. There are still unexplained phenomena in the world that we are discovering. Very recently, we found a substance in the natural world that behaves as a better superconductor than any material we have synthesized as scientists in a laboratory, and we don't know why. That's amazing. That is a point of emergence right there, right? And those are the places where I like to live, and that's where I like to do my work. And there are tons of complex phenomena in education that create opportunities for doing this kind of study. Learning to teach and being a teacher are both very complex phenomena. There's no recipe, there's no formula. Two people can do the exact same thing and get different results, even with the same group of kids. There are so many factors that go into making decisions about teaching and being a teacher and how you do things as a teacher. Same with medicine, same with being a counselor and working with other human beings to help them heal, psychologically heal, physically heal. Those are all very complex things. I showed you in mathematics, there are complex phenomena. And even in our field, just designing a learning environment, the number of decisions and factors we consider and weigh to come up with what is our best guess. I'm going to call it a guess. I don't know that we can predict, but we take a very educated guess at what's going to optimize learning based on all of those factors. One of my favorite quotes comes from Alan Schoenfeld. He is a math educator. He was president of AERA, which is our premier education conference in the country, not just our field, but across education. And he was president, and he made this speech, and they preserve the speech and they publish it. But this is one of my favorite quotes. He says, "Sometimes you have to build something to see if it will work. And without stopping, let me add, and then you have to study the hell out of it. We don't do nearly enough of that." And ever since I've read that, that has been like my goal and my driving factor as a scholar. I like to build things, and then I like to study the hell out of them. I like to see what emerges from them. I use theory to get a good sense of what I think ought to happen. But then there's also this openness in me and my methods and in my approaches where I say, I'm humble enough to know that I don't know everything. Let's see what happens. And that let's see what happens part of my work is really that's the fun part for me. So Carrie Valentine was my first doctoral student, and she and I, we spent 4 years studying the hell out of how children, middle school students, think about 3D and 2D perspectives and the relationship between them. We did it. We used the story of Flatland. If you're not familiar with Flatland, it's about a three-dimensional being that visits a two-dimensional world and what that experience is. And we thought, what if kids continued that line of thinking? What phenomena would they engage with where they're like, oh, there's a discrepancy here, or this is a real challenging or a problematic part of going from 3D to 2D world? And she pulled together a case library full of the tools and examples of what we do as human beings right now in this world to capture dimensionality, whether it's 3D or 2D or otherwise, and how we represent it and how we understand those relationships. And then we gave that to kids, and they wrestled with it. They created a game that blended 2D and 3D. There's a ton of them. So really fascinating stuff. And we ended up with a couple of publications, one of them just detailing the complexity of the design. It is a complex design. But then another one about how they embodied key mathematical concepts in their speech and in their writing and in their artifacts by engaging in this line of thinking with the support that we provided. Callie-Ann Newman and I, she was another doctoral student more recent than Carrie. She and I created this tool called Revision Assistant. It was meant to take old school proofreading edits and embed them in a Google document. We wanted kids to give each other feedback without actually fixing the document. We wanted to mark the problem, but not fix the problem, so that the writer could then engage in the fixing themselves. We wanted to separate that out. We spent 4 years. We worked with teachers, students. You can see this is Revision Assistant 2 because we actually have two versions. There's the first version that we tested and then the improved version, right? Studied that. We told the design story in one journal. We've got data in another journal. We studied the hell out of the phenomenon of writing schema and revision schema to understand better how we could create a tool that helped support that. And so when you think about my scholarship and what I do now currently, I like designing interesting learning environments and tools for those environments, and sometimes making new discoveries by looking at what happens at those points of emergence, not by slicing phenomena into small little bitty bitty pieces and testing each one. Not that there's anything wrong with that, but that's not where I like to live. That's not the work I like to do. I like to look at that point of emergence. I like to see new things, whether it's theory not working or theory working better than I even thought. Any of those are possible outcomes, and telling those stories are really interesting to me, and they have value and they have a place in our field. And so that's a little bit about me. I look forward to talking to you in person someday in the near future. And thank you for listening.